Hello and welcome. Let's take a look at another application of vectors, that of a dot product, which is used to calculate work done on a moving object. If a force causes displacement of an object, then the work done by the force is defined as the dot product of the force with displacement. As you can see, both force and displacement are two vector quantities. However, that dot product, which gives work, or the scalar product, would give a scalar quantity. So work is a scalar quantity in itself. So work is also equal to force in magnitude multiplied by displacement multiplied by cosine of the angle theta, where theta is the angle made between force and displacement vector. So let's take a look at an example number 4 in this case. So what we have in here is a 25 kilogram box. So here is the box, is resting 8 meters up a ramp. So it's right here, from here to down the ramp will be 8 meters. And the ramp makes an angle of 18 degrees with the horizontal, so as indicated on the diagram. We have to find the work done by the force of gravity as the box slides to the bottom of the ramp. So we'll write the formula. We know work is force times displacement. In this case, the force we're talking about is gravity, and displacement we're going to let be d. So alternatively, this would be the magnitude of gravity multiplied by the magnitude of displacement, and then the cosine of the angle made between gravity and displacement. So let's take a look at each and every part of this formula. So for gravity, we're going to say that is equal to mass times g. And here we have a 25 kilogram, 9.8 newtons per every kilogram. So 25 times 9.8 will give, here we go, 245 newtons. Now, displacement, on the other hand, since we're told that it's 8 meters up the ramp and is going all the way down due to gravity, that means that we have 8 meters for displacement. Now, angle theta is the angle made between these two vectors. So let's take a look at both vectors here. So we have displacement, which should start right here at the center of the box. And we have the gravity vector. So let's label them on the diagram. We're going to say that the angle made between gravity and displacement would be this angle theta right here. And if you build a triangle, you can imagine dropping a perpendicular in here. We have this angle 18 degrees. This is 90, which will make theta 90 less 18. So 90 minus 18, or 72 degrees. So now we're ready to find work, and we're going to say work equals 245 multiplied by 8 and multiplied by cosine of 72. And here we go, just put them on in the calculator, so cos 72. Make sure your calculator is set to degree mode, since we're using degrees, obviously. And here we go, 605.67, so 0.7. So 605.7. So now let's talk about the unit measurement. So you know that you see that gravity is measured in newtons, it's force, and this is displacement in meters. So two ways of describing, or for the unit measurements of work, we can either say Newton meters or we can use joules. So 605.7 joules. And this is the answer for the first part of the question. Now the second part of the question is quite interesting, and it's very much related to physics, but we know how they go hand in hand. So we have to find the minimum force that is acting at an angle of 40 degrees to the horizontal that is required to slide the box up the ramp. So the force that we're looking at is a force that we apply at the bottom of the ramp here. And we're going to say that we can apply some force at an angle of 40 degrees. Maybe that's what physically convenient or available. So that's what we can, the direction of the force we can apply. Now, if the force that we're applying makes an angle of 40 degrees with the horizontal, it means that the angle between the head of the vector, the displacement vector, and the tail of the force that we are applying is about 22 degrees, because this is 40, take away 18, that's 22. Now, we need to find the minimum force that will bring the box up the ramp, which means that this will be the force that will bring the box from the very bottom, where it has comes down due to gravity, to the top. So I want us to think about it for a moment. So if we want to find out the force that brings the box up the ramp, that would be the same as if we had the box up the ramp and we were thinking of applying a force that would keep the box stationary or not moving. So in other words, we're going to say bring this force of which we have indicated by FA up here. I'm going to make this kind of look parallel to this. Let me try to do it a little bit differently. Okay, and I'll bring this force right here. So what that means now is that we have changed up the problem a little bit. So we have gravity going this way. We have this force that we are thinking of applying to the box, so it won't move. And we also have the normal force, which is not indicated here, but we are going to draw it. It's perpendicular, always perpendicular to displacement. So these three forces, so the gravity, the force that we are going to apply to keep the box in place, and the normal force, which is a counteracting force, right, applied on the surface, would be in equilibrium if the object is not moving. So what we're going to do is we're going to try to bring all these three forces in the equilibrium triangle. I'm going to start off with the first one, which is the gravity. The gravity is easiest to draw. So I'm going to draw the perpendicular or the vertical line that represents gravity. Again, vectors are not to scale in here. And the next thing that I want to do is bring the force FA. Now remember that in the equilibrium triangle, we place the vectors head to tail. So what I'm going to do in this case is play a little bit with the diagram, because I want to figure out what the angles are exactly. So if I had the force FA right here and drew the gravity with tail at the head of vector A, then I will have to think of what angle this is going to make, or they're going to make together. So here we go. We're going to have gravity going down here. So that would make this angle, this is 40, so this is 90, so this would be 130 degrees. So if this angle is 130 degrees, and I decided to bring gravity now with the head, at the head of FA, then I would say that this angle right here then, okay, remember that we have a C pattern, right? So if this is 130, then this must be the supplementary angle, so 50 degrees. So we're going to say that if gravity and FA are placed head to tail, that means that they will make together an angle of 50 degrees. So here goes the force FA, and here is the angle 50. So let's take a look now at the normal force. So I'm going to bring the normal force. So the normal force has to go with the tail at gravity and the head at the FA, force FA. So we want to bring, in other words, the head of the normal force to the tail of gravity. So we want to bring it somewhere in here. So this would be okay, so this would be perpendicular again. Remember, this would be perpendicular to the ramp. There you go, that's the normal force, and it will be perpendicular to the ramp. So that will make the angle head to tail with the force FA equal to, so again, look at this angle, this is 90. This angle here is 22. So the angle made between the normal force and force Fa, when placed head to tail, would be 90 plus 22 or 112. So we'll have the force Fa equal to 112 degrees. Okay, so here we go, force Fa. This would be the normal force, which we are going to indicate by the force N, by letter N here, and we have gravity as well. So we are going to make the triangle look a little bit more organized, and voila, we got the triangle. We have almost every angle possible here. So we have one angle 112, 150, so that will make this little angle 180. Take away 112 and take away 50, so 130 minus 112, that's like 30 minus 12, and 30 minus 12 would be about 18 degrees for this angle. So once you have the equilibrium triangle, you just use the sine law to find the unknowns. Remember that gravity will be mass times g, and that would be 25 times 9.8. We already found that for the first part of the question, which was 245 newtons. So in this case, what we're looking for is the force Fa, and we're going to start off by writing the sine law, which is force Fa in magnitude, obviously, divided by the sine of the angle opposite to Fa, which is an 18-degree angle, sine 18, equals gravity, which is 245, divided by the sine of 112 degrees. So just simply cross multiply to find or to solve for Fa. So I would say that the magnitude Fa equals 245 sine 18 divided by sine 112. And just use a calculator again. 245 sine of 18 divided by sine of 112 gives 81.65 newtons. So about 82 newtons, we would say. So we're going to say that we're going to need a force of above greater than 82 newtons in order to be able to slide the box up the ramp. So I hope that this made sense and you found it useful. Thank you for watching. Bye for now.